In graph 24.12, we considered what average payoff pairs for two players playing an infinitely repeated prisoner's dilemma game are possible if we could simply dictate the sequences of cooperation and non-cooperation that the two players would engage in. We'll now turn to considering which of these pairs of average payoffs could emerge as a subgame perfect equilibrium in the infinitely repeated prisoner's dilemma game depicted in panel A of graph 24.12. If both players play the strategy never cooperate, then the average payoffs for the two players will be 5 each. This is a Nash equilibrium of the infinitely repeated game, because if my opponent never cooperates, it's a best response for me to never cooperate. It's furthermore a Nash equilibrium for every subgame of the infinitely repeated game, which itself is an infinitely repeated prisoner's dilemma game. Thus, the average payoffs of 5 each can certainly emerge in a subgame perfect equilibrium to the game. Next, consider the fully cooperative outcome pair of 10 each, an outcome pair which would emerge if both players always cooperate every time they meet. Suppose the two players adopt trigger strategies that say cooperate the first time we meet and continue to cooperate every time we meet unless someone has defected at some previous stage. If both players adopt this strategy, both players will always cooperate, and the present discounted value of getting a payoff of 10 every time we encounter each other is given in equation 24.9. These are then Nash equilibrium strategies for the game if neither player can benefit from deviating. If player 1 deviates and player 2 plays the trigger strategy, then the first time player 1 deviates, he gets a payoff of 15. But every period thereafter, the two players will both not cooperate, each receiving a payoff of 5. The present discounted value of this to player 1 is then given in equation 24.10. You can then easily show that equation 24.9 is greater than equation 24.10 so long as delta is greater than 0.5. In other words, so long as the players don't discount the future too much. This implies that the trigger strategies we've specified are in fact Nash equilibrium strategies for the infinitely repeated game. And we can also show that they're Nash equilibrium strategies for every subgame of this infinitely repeated game. Such a subgame falls into one of two possible categories. The subgame either occurs with cooperation always having occurred prior to the subgame, in which case the subgame is identical to the original game, and the trigger strategies we've just shown to be Nash equilibria to the original game are also Nash equilibria in that subgame. Alternatively, the subgame might be one where a defection has previously happened prior to the subgame being reached. In that case, the strategies would imply that both players will not cooperate forever, and we've already shown that that too is a Nash equilibrium to the infinitely repeated game. We've therefore shown that the trigger strategy that starts with cooperation and punishes defection with non-cooperation from then on is in fact a subgame perfect equilibrium strategy for both players in the infinitely repeated game, assuming that neither player discounts the future too much. In graph 24.12, we then illustrated that we can construct sequences of cooperation and non-cooperation such that any average payoff pair that lies within the diamond shape here can in fact emerge. But we now ask which of these can emerge as a subgame perfect equilibrium outcome. We know that no player could possibly get a payoff of less than 5 on average in any subgame perfect equilibrium, because the player could simply never cooperate and guarantee himself at least a payoff of 5. But we also know from our work in graph 24.12 that any average payoff combination in the shaded area can arise from a properly specified sequence of cooperation and non-cooperation in the infinitely repeated game. We can then take any average payoff pair in the shaded green region and specify the sequence of cooperation and non-cooperation that leads to that average payoff pair. And we can specify strategies for the two players such that they either play along those sequences or non-cooperation forever is triggered. The same argument that allowed us to conclude that full cooperation always can emerge as a subgame perfect equilibrium and result in average payoffs of 10 for each player, then allows us to also conclude that any of the shaded average outcome pairs can occur in a subgame perfect equilibrium with a trigger strategy, so long as neither of the players discounts the future too much. Of course, the closer that the average payoff gets to the non-cooperative payoff of 5, the less a player can discount the future in order for that payoff to still be able to be sustained in the subgame perfect equilibrium. The possibility of all of these average payoff pairs emerging as part of a subgame perfect equilibrium, assuming no heavy discounting of the future, is then known as the Folk theorem, as applied here to an infinitely repeated prisoner's dilemma. And this Folk theorem logic can also be applied to other infinitely repeated games.